I would like to start the presentation about the topic of eigenvalue and eigenvector. So I would like to start the presentation by introducing the definition of eigenvalue and eigenvector. So let A be an n times n matrix if there exists a real value lambda and a non-zero n times 1 vector x that will satisfying the equation of ax equals to lambda x. So we can refer to lambda as eigenvalue of A and x as an eigenvector of A. So let's come to the example of application of eigenvalues and eigenvectors. When studying vibrational problems where the eigenvalues represent fundamental frequencies of vibration and eigenvectors characterize the corresponding fundamental knot of the vibration. Now let's come to finding eigenvalues. After we get the equation 1, which is the eigenvector equation, ax equals to lambda x, we can rewrite it in the form of equation 2, which is a minus lambda I times x equals to 0. We can get this equation by moving the lambda x to the left side and multiply the lambda with the identity matrix, where the I is the n times n identity matrix. And we know that a minus lambda I in the equation 2 is not invertible. So the determinant of the a minus lambda I is equals to 0. And we call this equation as characteristic equation. Now let's come to the example on how to find the eigenvalues of the matrix. Now we are given a 2 times 2 matrix A. So the first step to find the eigenvalues of the matrix is to use the characteristic equation. The characteristic equation is the determinant of A minus lambda I equals to 0. And we know that I is an n times n identity matrix. So in this case, I is the 2 times 2 identity matrix. Therefore, we can substitute the value of identity matrix and the value of matrix A to get the value of lambda. So we get the value of lambda is equals to 0 and lambda equals to 4, which means that the eigenvalue of the matrix A is equals to 0 or equals to 4. Now comes to how to find the eigenvector of the matrix. So here is the example. Given a 2 times 2 matrix, which is matrix A. So before we find the eigenvector of matrix A, we have to find the eigenvalue of matrix A first. So we are using the same method to find the eigenvalue of matrix A. So we are using the characteristic equation, which is determinant of A minus lambda I equals to 0. In this case, the identity matrix is 2 times 2 identity matrix. We substitute the value of identity matrix and the value of matrix A to get the eigenvalue. So in this case, the eigenvalue is equals to -3. Since we get the eigenvalue, which is lambda equals to -3, we can substitute back the eigenvalue into the eigenvector equation to find the eigenvector. So in this case, we substitute lambda into the equation and we get A minus -3i times x equals to 0. Then we can substitute the value of matrix A and the matrix of identity. After that, we can get the linear equation by the matrix multiplication. So the linear equation we get is x plus y equals to 0, y equals to -x. And we assume x equals to a constant, which is k. So the linear equation will become k plus y equals to 0 and y equals to -k. Now we can factorize the constant k from the matrix x, and we get the corresponding eigenvector is 1 and -1.
This video is talk about what is a vector space. Vector space is a non-empty set with two operations, which is vector addition and scalar multiplications that satisfy the following properties. This slide is talk about what is the vector addition and what is the scalar multiplication. We call it as a metric space. So V equal to M, M multiply N. For example, let's say M equal to N equal to 2. So M 2 multiply 2 means that we have a 2 row and 2 column. So for the vector addition, we need to use A plus E equal to A plus E, B plus F equal to B plus F, C plus G equal to C plus G, D plus H equal to D plus H. Whereas for the scalar multiplications, we need to sub this Z into this matrix. So Z multiply A equal to ZA, Z multiply B equal to ZB, Z multiply C equal to ZC, Z multiply D equal to ZD. Let us look at this example. Let U equal to 2150, V equal to 431 -1, and W equal to -6203 be vectors in R power 4. So for x in 3 bracket x plus W equal to 2U minus v plus x. Solutions. Based on the distributive properties, we can sub 3 into this bracket, which will become 3x plus 3w equal to 2u minus v plus x. Then we move the x to the left hand side and the 3w to the right hand side. Become 3x minus x equal to 2u minus v minus the 3w. Then 3x minus x will become 2x. Then this we all copy back. Then this all we divide by 2. Then become x equal to u minus 1 over 2v minus 3 over 2w. Then we sub u, v, w inside this, and then we can get a final answer.
For now, I'm going to show what is subspace. A subspace is a term from linear algebra and is a space within a vector space which satisfies two criteria. And now you can see the first one picture, and the scalar is multiplied by a big scalar and becoming longer. But the scalar is not within the yellow area, so it is not a subspace. For now, you can see the below. The line is go through but not go through the origin, so it's no zero vector. So zero vector is not in the space and it can not multiply by any scalar, so it is not a subspace. From the right hand side picture, you can see the first one, the line is go through the origin. Either you add vector or multiply the scalar, it always is a subspace. And the below picture, the yellow area is covered by all the area. So you can add any vector will stay within the plane. And since the plane goes infinity in all the directions, so the scalar is always is subspace. Okay, for subspace, we need to have three conditions. First condition is zero vector. We can see the W can be zero vector or not. Yes, it can be zero vector. So it is achieve the first condition. And the second condition is closure addition, U plus V. So we take A minus A, 2A plus A minus A, 2A will equals to 2A, 0, and 4A. And so since it can addition, so yes, it's achieved the second condition. And the third condition, closure multiplication, CU, as a constant, C multiply A minus A, 2A. Is that it can multiply? Yes, it can multiply. So it achieved the third condition. So it have achieved the three conditions. So W is a subspace of V. Summarize, when you are doing the subspace questions, you need to determine it can be zero vector or not first, and then if achieve the condition, and then you can make sure it can vector addition u1 plus u2, and then you want to see it can multiplication and the constant is good, is okay or not. So if three conditions are satisfied, there are a subspace.
Now we discuss about the linear combination of vector. What is linear combination? Linear combination is an expression constructor form a set of terms by multiplying each term by a constant and adding the result. As the example at here, we can see x and y is the terms, ABCD is the constant. Then the linear combination of vectors is a sum of scalar multiple of those vectors. Like here, V is linear combination of vectors v1, v2, and v3. And the C is the coefficient of the linear combination. Now look the sample question at here. We need to write the linear combination of matrix A in terms of these three matrices. First, we need to construct an equation by the constant A, B, and C. Now, we multiplying all the matrix element by the constant A, B, and C. First, A times 3 plus B times 2 and C times 2. We could get 60. Then we multiplying the following element with the constant. We could get 4 equations at here, and we try to find the A, B, and C. After get the value of A, B, and C, we write the linear combination of A again with the value we get.
So next we will discuss about what is span. So we suppose that we have a set of vector S equal v1 until n, then the set of all linear combinations of this set is called span, and we denoted it by span S. So we take a look at this example. If set uv where u equal 3, 2 and v equal 5, 7, then we can write down the span of vector span set uv equal alpha times 3, 2 plus beta times 5, 7, where alpha and beta is our coefficient, and this is similar to our linear combination form. And we can write down the span of the set in general form 3 alpha plus 5 beta and 2 alpha plus 7 beta. We can let alpha and beta be any value and find the matrix that satisfies span. Next, we will need to show a matrix belong to span of a set of matrices. So we have M equal 47 and 17, and we need to show is the span where S equal 5, 2, 3, 1. So the solution is we write it out in linear combination form. 47, 17 equal alpha times 5, 2 plus beta times 3, 1, where alpha and beta is our constant, or we can say is our coefficient. Then we can obtain simultaneous equation from this linear combination form, where 5 alpha plus 3 beta will equal 47, and 2 alpha plus beta will equal 17. Next, we will need to solve this simultaneous equation. We can get a value of alpha, which is 4, and beta, which is 9. Then we can write down the linear combination 47, 17 equal 4 times 5, 2 plus 9, 3, 1. So this shows that M is linear combination of all vectors in set S. So M is subset of span S. Why we say M is subset of span S? Because there are many other matrices that we can write it out in this linear combination form, but with different coefficient alpha, beta. The alpha might be 1 and beta might be 2 or something else.
Now we come to the next subtopic, which is linearly independent. So what is linearly independent? Two or more vectors are said to be linearly independent if none of them can be written as a linear combination of the others. On the contrary, if at least one of them can be written as a linear combination of the others, then they are said to be linearly dependent. As we can see here, a set V1, V2, V3 until Vn is linearly independent if C1 times V1 plus C2 times V2 plus C3 times V3 plus until Cn times Vn equal to 0. For all C1 equal to C2 equal to C3 until Cn equal to 0. If not all C1, C2, C3 and so on are 0, such that C1 times V1 plus C2 times V2 plus C3 times V3 plus and so on equal to 0. So we can say that a set V1, V2, V3 and so on is linearly dependent. Now have a look at the problem statement 1. Show that the vector p equal to 5, 9, 3, 1 and vector q equal to 0, 0, negative 8, 4 are linearly independent. For the solutions, let C1 and C2 are constant, such that C1 times p plus C2 times q equal to 0. As here, we can easily think that C1 equal to 0 and C2 equal to 0, since C1 equal to C2 equal to 0, so we can conclude that P and Q are linearly independent. Let's move to problem statement 2. Show that the vector 1 equal to 2, negative 1, 1. Vector 2 equal to 3, negative 4, 7. And vector 3 equal to 7, negative 6, 9 are linearly independent. For the solutions, let C1, C2 and C3 are constant, such that C1 times V1 plus C2 times V2 plus C3 times V3 equal to 0. We can verify that the solution of these matrix equations are C1 equal to 2, C2 equal to 1, and C3 equal to negative 1. Since C1 equals to 2, C2 equal to 1, and C3 equal to negative 1, so we can conclude that V1, V2, and V3 are linearly dependent.
To sum up, here is the way to find eigenvalues of space, span, and linearly independent, and here is the properties of vector space.